Hello. Hi, everyone. I'm Victoria Turk from YGK. It's an absolute pleasure to be here at VivaTech for our session now on the quest for a quantum advantage. So if you were here for Whirly sessions before, you've got a little bit of a grounding in quantum computing and why everyone's talking about it right now. We're going to get into some more of the reasons of why people are so excited about quantum computing and the applications that it will have. Now, before we begin, I'm just going to ask each of our panelists to give a very brief introduction to what you actually do. So let's start at the end. Sophie Proust, you're Chief Technology of Atos. Tell us more about what your role in quantum is.
Okay, so hello everyone. So just to tell you, for those who don't know, so Atos is a leader at providing services to customers, end-to-end solutions regarding their digital transformation. And as part of the digital transformation, you know, there is very much about power computing. And so this is how we arrived to quantum computing. So we decided 3 years ago to start there. And we have been developing a quantum learning machine which enables us to deliver to our customer the ability to develop programs and also to run on the emulation of a real quantum qubit.
Fantastic. And Vinet, tell us what you're doing at CEA.
Hi, everybody. So at CEA, what we do, we are a research technological organization. And I'm an engineer, and I have a PhD in physics. And what we do together with the team is that we're trying to build a quantum processor made out of silicon. We're trying to leverage all the history that we have in building devices for Moore's law to actually build a quantum computer. So we're aiming at 100 qubits within 6 years, and to identify the key roadblocks to go to scale up.
Fantastic. And last but not least, Talia Gershon, IBM. What's your role there?
Perfect. Hi, everyone. So I'm Talia Gershon. I'm the Director of Research Strategy and Growth Initiatives at IBM Research. And at IBM Research, we've been working in the field of quantum computing since some of the earliest days of the field. And we have our full stack quantum program, everything from quantum hardware and actual systems, all the way up through software, through applications, algorithm development, and we also have a very robust community program to drive education and to help people learn about the field. So everything from innovations all the way up the stack.
Fantastic. Now we've got to know you a bit better. Let's start our discussion. We will be using the Slido app to take questions, by the way. So if you've got questions for any or all of our panelists, do submit them via the VivaTech app or at slido.com. You don't have to wait till the end. We'll pick them as we go along. We'd love to hear what you want to know about so we can make this session as useful as possible for everyone. Now let's start at sort of the most fundamental question, I guess. Which is, why do we want quantum computing? Whirly before said, it's not just about making things faster. This could really revolutionize several fields. What are some of the key applications that you see quantum computing having a major impact on?
Perhaps I can start there. So why do we need quantum computing? So actually, I would say we need quantum computing for two main reasons. The first one is the nearly end of the Moore's law, this law which tells us that we will be able to gain double the performance of the systems every 2 years. So we know we're getting to an end because the print we are now in is 7 nanometer. At 5 nanometers, quantum effects on transistors will appear, and then it won't work anymore. So we really need to find a new technology to gain more power. Then the question would be, why do we want to gain more power? Well, because, today's applications are requiring more and more power. For example, we've seen with artificial intelligence, with big data. So we really need to have more powers. So quantum computing is an answer. It's not the only one. There may be others. But it's an answer. And we think that today, and it's still in the research area, like it was presented before. It's in the research area in the hardware, but also in the software. Because you were asking about applications, we know that there are certain kind of algorithm which are really fitting what we will be able to do with quantum computers, but we still need to research for more.
Yeah, exactly. So to add to that, I think it's important to know that quantum computers are not going to be useful for every kind of problem. There are specific kinds of problems that we think will be better solved or solved faster on a quantum computer. Some examples of that are chemistry simulations. So why are chemistry simulations really hard on a classical machine? It's because simulating quantum effects, you have to take into consideration the influence of every electron on every other electron when two atoms are bonding together, for example. So the bigger the molecule you're trying to simulate, the more electrons, that problem can blow up exponentially. But we think that it'll be faster to simulate a quantum system using a quantum system. There's a way to describe that problem more efficiently and to solve it on a quantum computer. And other examples would be, for example, Sophie mentioned AI. There's other examples like optimization problems that we're exploring, problems in chemistry and in finance, for example.
And well. Mode, CEA is a research institute, right? So what sort of things are you looking at?
Sorry?
What sort of applications are you looking at CEA?
Well, I think the points that Talia are pointing are really good in terms of optimization. These are the first applications within reach of a quantum computer, the combinatorial optimization problems, and there are a lot of problems that can be mapped on with these problems. And the quantum chemistry, of course, that's the original idea from Feynman, to use quantum computer to actually describe quantum physics. So this is within reach, and it's actually solving a lot of problems that Sophie was pointing out, where with the current computing power, we cannot solve, and we're spending a lot of energy where we cannot compute in a competitive time. So what quantum computer is going to bring is really be able to solve a certain class of problem that are not tractable today.
And perhaps I can just add, if people want to know and see what kind of algorithm exists, the NIST is listing all them. And if you Google Quantum Zoo, you will see all the algorithm available today.
Quantum Zoo, great. You mentioned, that quantum computing is very much still in sort of the research stages, and there is a lot of hype around it and a lot of kind of mythology. What is the truth? What stage are we actually at, and when will we actually have a quantum computer?
You put online a quantum computer, so you should be the first.
Yeah, maybe let me start and then feel free to chime in. So a couple of years ago, 3 years ago, IBM Research placed a quantum computer available online for the first time. It was the first time that anybody took a prototype system and made it available through the cloud. And that system had 5 qubits at that time. Since that time, we've added another 5-qubit machine, a 14-qubit machine, 20 qubits. We're working on 50 qubits as well. And I think Worley mentioned, number of qubits. He mentioned working with NIST and other agencies to really be able to create standards, because not all qubits are created equal. So I think it's really important that when we talk about qubits, we don't just talk about qubit number. We talk about something that, we're pioneering a measurement type we call quantum volume. So quantum volume takes into consideration not only number of qubits, but also effective error rates. So when you go and you perform operations on the qubits, those operations are not always perfect, right? So you want to know how accurate are these operations in actually creating the effect that I'm trying to produce. And it also takes into consideration connectivity between the qubits, because if I want to couple 2 qubits, how many operations do I have to do in between this qubit and that qubit to create that entanglement, for example? So quantum volume is an example of a kind of measurement that we could use across the board for many different kinds of quantum systems to benchmark them. So, it's really important to do that. From a research perspective, by putting these systems online, we could actually see the different kinds of algorithms that people are trying to develop and actually facilitate a faster rate of discovery of new quantum algorithms. So one thing we observed is since that time, we've seen 160 research papers that have been published using the IBM Q experience, everything from applications in chemistry, AI, finance, optimization. So you can really see algorithm development and exploration, because I think that we're going to discover many new things that you can do with a quantum system once you actually have a quantum system. And then the last point on kind of Where are we really? Worley also talked in his presentation about getting ready for a quantum advantage. So for many industries, if I gave you a quantum computer with 1,000 qubits, you may not even know what to do with it, right? So there's a period during which time the hardware needs to advance, the software stack needs to advance, and Worley mentioned our software stack called Qiskit, and the algorithms need to advance all at the same time so that when we actually have systems that can achieve a quantum advantage, that people are prepared to know how to use them.
Well, thank you, Talia. So just to add another perspective from a hardware perspective, Worley showed you numbers, and actually we are in research at the stage where there are a couple of experimental platforms that have demonstrated qubits. And we don't know yet which platform is going to be the one that's going to be used at the end. The quantum computers that we have, it's kind of a big word for a few things that they can do, because what they have actually demonstrated is factorizing 15, which we can all do, for instance. But what is very interesting, it's not what we currently have, it's also the rate at which we are making progress with respect to the perspectives that we will have when we will have a few qubits, hundreds or thousands of qubits. So that's really what makes it exciting. At the research level, we are currently solving problems, and we're making proof of concept. And one by one, we're tackling all the problems that we actually know. We're moving fast, and at the same time, the software and application people are telling us, oh, this is the kind of problem that you can solve if ever you have the hardware. And this is what makes the field very exciting currently. This is really the perspective and the pace at which we're making progress.
Yeah, absolutely. So I fully agree. So the problem now is to scale and to have clean fidelity qubits. And I think what's interesting on the application side is now the question is more, from a given algorithm, how many qubits do I need to solve a problem, rather than going to a race of a lot of many qubits. So it's more focused on the application side to see which problem we're going to be able to solve, and this will require how many qubits.
So when do you think people who might be sitting in the audience today who aren't researchers, don't work in research facilities, when will they be able to use a quantum computer? When will this become something that individuals and businesses actually have access to?
Today already, right? So we made these systems available online because we really felt that, for people to actually figure out how to use it, it's a very important tool for education. So, the answer to when you can all access a quantum computer is already, right? It's 3 years ago. But I think your question is more, when will you use it but not know you're using it? Or when will you use it to solve a problem that you can't solve today? So the answer to when you're going to solve a problem you can't solve today, we talked a lot about how, we need to increase qubit fidelities. We need to discover new algorithms. I think over the period of the next few years, we're gonna reach a point in time where we're gonna have systems that are sufficiently powerful and software that's sufficiently powerful, and have discovered algorithms that are sufficiently useful to actually achieve that. But I think it's the right time to start learning. So one of the things that you can learn from the history of regular computer science and the rate of progress in the field of computing at all was some of the early adopters, they had to learn to write in assembly languages if they wanted to be able to use early systems. They didn't wait until the software abstracted away all the complexity of the systems. They actually wrote assembly code. And that's kind of where we are now, and we're also reaching increasing levels of abstraction in the software stack. But if you are willing to learn how to use quantum assembly, for example, you can start to do things that you can start to experiment with new kinds of problems. But as we make progress to abstract away the complexity of circuits, right? Hierarchies of circuits to just say the higher level thing that you're trying to accomplish, that's going to be the point in time at which more people will understand what to do with these systems.
So now is the time to get started.
I think so.
But yeah, what I would add perhaps is that we are not really talking about quantum computers now. We're more talking about accelerators. And so those kind of small entities with qubits where you will be able to offload part of your program to get the quantum speed up.
And maybe, so today is the day for the geek people to get involved with these quantum accelerators. But at the end of the day, the way we project, the way we see the quantum computer for the users is maybe that they won't know that they're using a quantum computer once we've been able to devise a workload on the appropriate accelerator.
Great. Now let me take a couple of questions from the audience because we're getting quite a few through. So thanks everyone who's submitted one so far. We've got one at the top here. Do you think that quantum computing could help for tasks that now need to parallelize, like graphical rendering? Anyone got insight on that? I'm not going to pretend to completely be able to understand that question.
So I think this question probably stems from GPUs, right? Developing for the purpose of doing graphical processing, which is a task that needs to be highly parallelized. I think you could think about today the way we compute is if we have a really complex problem that we try to break it apart and solve pieces of it in parallel. I think quantum computing works just differently than that. So, just brief description, and feel free to, interject and add on top of my description. But the way a quantum computation works is you don't do the same thing that you do with classical computing, but faster. You compute in a fundamentally different way. So if you imagine creating a quantum state, you actually create and prepare a quantum mechanical state, and then you manipulate that state. So the first thing you do is you need to kind of encode the problem that you're trying to solve into that quantum state. So now you have a quantum state that represents the problem you're trying to solve. And then your algorithm proceeds by manipulating that state towards a solution to your problem, and then you measure the state. So it's a very different form of computation that requires fundamentally thinking differently about how do you describe the problem in the form of a quantum state that you could prepare, and then what are the series of operations that you would perform on that state to drive it towards the solution to the problem, and then you take a measurement of the state, and you collapse that state into something classical that you can measure.
Absolutely. So it's, as you said, the paradigm of programmation completely changed. It's more a statistical way also of programming. And actually, this is why we developed the quantum learning machine, so that people get accustomed, because it's completely different from the serial way of programming we used to do. So we have several gates, as you said, and we need to manipulate all those to create a circuit. And so, yes, so I think those kind of tools are very useful to get into the mindset of what is quantum computing.
Maybe to try to provide a picture. This is a very simple picture, but it has proven to be efficient in the past. I'm not a specialist in graphical rendering, but in quantum computing, what we rely on are two properties, integration and superposition in physics. And if you look at something that you're more familiar with, you think of going out of a maze. You've got a problem, and the problem you're looking to solve is going out of a maze. A quantum computer at each intersection can go both ways. This is a superposition. And then, because of intrication, when you are within the maze, you know what's happening at each intersection at the same time. So it provides you with an idea. You understand intuitively that you will find the exit of the maze much faster than looking at each intersection one after the other. And this is this kind of problem. Quantum computing relies on matrix formalism, and this is this kind of problem that definitely finds a speed up with quantum computer.
Great. So it sounds like there's lots and lots of potential applications, but it's better to think of it as a whole new paradigm rather than thinking of just improving on current processes.
I think that's right. There's one more description of a quantum algorithm I thought was really powerful that I learned from a professor at the University of Maryland. So if you imagine your algorithm as, a wave moving towards a shoreline, right? So if you just put the whole system into a superposition, then when the wave hits the shoreline, it's an equal amplitude everywhere. So it doesn't meet the shore in one particular place, it meets everywhere. So that's not really going to help you solve a problem. If the answer is all of the answers, that doesn't really help you, right? So what you want to do is you want to place boulders in the ocean to shape the wave so that it crashes at a particular point on the shoreline. So it's kind of an analogy to think about. You're controlling the amplitude of the quantum state in particular places that represent the answer to your problem.
Great. Nice visualization there. Thanks, Talia. Now, another question, I think this is quite an important one as well, given the climate that we live in. What is the potential environmental impact of quantum computing in comparison to standard computing? Can it help to reduce environmental impact, or could it have the opposite effect?
I would say reduce, but I will let you. No, but I think in terms of power consumption, it's really much lower. So perhaps you can elaborate.
So the power consumption today, I'll describe our approach to quantum computing, which is a superconducting quantum chip. So, we process qubits on a silicon chip, and they're made out of superconductors. And the way that we control it is we put it inside what's called a dilution refrigerator, which is a very, very cold, it's a way of making this chip very cold. It cools the chip down to about 15 millikelvin. So you can imagine that's about 100 times colder than outer space. It's very cold. So the power that we consume is actually mostly in cooling the processor down to a temperature where you don't have interference from stray radiation and you don't have things that are going to decohere your quantum state. And then we basically put control coaxial cables, that go down to the bottom of the dilution refrigerator, and they apply operations on the qubits to control the state and to read the state. So most of the power consumption is actually in cooling. So, a single dilution refrigerator today can hold about 50 qubits. Over time, you could imagine getting to 100 or a few hundred qubits. So a single dilution refrigerator, to cool that chip down, it's going to consume a lot less power than something like a giant, Summit system with 9,000 CPUs and 27,000 GPUs. It's a much smaller, more compact system, but again, it doesn't solve all the same kinds of problems. So you gotta think about the problem you're trying to solve.
To answer from a research perspective, this is an actual research problem, the energetics of quantum computing, because we've got the system, but we've got the calculation by itself, and there's on one hand. We've got an exponential speed up. So if you just think like that, you can reduce exponentially the number of operations, so done. You've saved some energy. But on the other hand, you might have to correct from quantum errors, and we don't know yet how to measure and how much cost this correction will cost. So this is actually something we are willing to decrease. When we build a system, we want to decrease the energy consumption, and we want to make the quantum computer competitive with respect to current calculators. But this is actually a research question.
Great. Well, I'm glad to hear that people are actually taking it into consideration, at least anyway. Now, we've got a question. I think someone asked earlier a similar thing about hacking. So when will quantum computing be powerful enough to break common encryption algorithms protecting most of our internet and e-commerce? So basically, I guess, does quantum computing pose a threat on the security front?
Go ahead, Sophie, go ahead.
Just to say that it's true that the Shor algorithm, which enables to factorize prime numbers, this is how the keys are computed, was found a few years ago, and this is what regained, some enthusiasm about quantum computing, because we've seen an application. So Shor demonstrated we could do that, but it's true that then it's a threat. The thing is, you will need thousands of qubits to break a key. So.
Yeah, that's right. So I think Shor's algorithm is what everybody's really stressed out about, is like this idea that we're gonna be able to factor numbers. So it's gonna take millions of fault-tolerant, error-corrected qubits to break today's RSA with a quantum computer. So that's an important distinction. So this error correction concept. We take it for granted in classical systems that, our computers, they have errors, but we've come up with error correction schemes. So you take your data, you duplicate it, and then you say, 2 out of 3 times this was a 1 instead of a 0, so we're going to call it a 1. You can't take those measurements and duplicate information like that with quantum systems, because it would collapse your quantum state and you'd lose your information. So you need a different scheme to correct quantum systems than you need for classical systems. And the schemes we know about today are it takes 20 times the number of qubits, physical qubits, to get to a single logical qubit. So very, very quickly, you need 1 million or several million qubits to break RSA with Shor's algorithm, but very quickly, if you need to error correct them, you get these even higher numbers. So it's going to take some time based on algorithms that we know about today and error correction schemes that we know about today.
So we don't have to worry quite yet.
But in between now and then, there's tons of applications for new business value that quantum computing will unlock, right? So that's the focus for us.
Great. We're running out of time. It's gone very quickly. So I'm going to end with one last question. Obviously, we're in Paris, and we've got two representatives here from France. What is the French ecosystem like for quantum computing? What role does France have in this sort of global challenge?
Well, the French ecosystem has the chance to have very, very renowned French scientists in terms of quantum physics. France demonstrated, for the first time, Alain Aspect in 92 demonstrated the entanglement of two particles, which is the root of the current second revolution, and which is the foundation for quantum computing. So we've got this ecosystem. We also have a very vivid research and technological organization, and we've got an industrial ecosystem of semiconductor. What is currently going on is that we are just setting up a collaboration at the country level where we try to interconnect all together, and we'll try to leveraging at the same time the hardware and the software and the system level, because we think that there is a space for co-innovation which is going to speed up the construction of a quantum computer.
Okay, absolutely. So you're right. I mean, we've got great academies. We could also cite Serge Haroche, who had the Nobel Prize. So a lot of universities are also very much involved. We are working with them. We are working with CEA. We are working indirectly, but with IBM through Oak Ridge. So yes, there is a lot of things. And Europe also is investing a lot in quantum computing. So there's a lot of future for that.
And to add one thing, we also have a university partnership with the University of Montpellier. With Ginny mentioned this morning, we have a whole network of partners called the IBM Q Network, and we just launched a new hub of the IBM Q Network at the University of Montpellier to create an ecosystem with access to our most advanced systems, working in partnership between the university and various industrial partners also in France.
Yeah, just to bounce on what Talia said, France is getting structured, but is not isolated. We are not doing the Minitel. We're actually aware that this is an ecosystem, as Worley was saying, and there are worldwide and collaboration, an initiative at the EU level, which is a quantum flagship, and France is very active at all levels.
Great, lots going on. Thank you ever so much, Sophie, Maud, Talia, and here's to a quantum future.